Hi, in this video we are going to talk about the concrete implementation of the Hamiltonian cycle problem. So let's get started. First of all, we are going to have two main classes, the app.java and the Hamiltonian algorithm.java. And of course, this app.java is just good for testing our algorithm. So here, for example, we will going to test our algorithm on a simple graph like this. We have 4 vertices. All of them have 2 degrees, and which means that both of the vertices has 2 edges, and it's very easy to find Hamiltonian cycle even without any programming code. So for example, 1, 2, 3, 4 and back to 1, it's going to form a Hamiltonian cycle. Why? Because we are going to visit every vertex exactly once, and the starting point is equal to the end point. So, as we have discussed earlier, we are going to construct the adjacency matrix. We are going to represent a matrix with a 2-dimensional array. And of course, each of the rows, for example, this row is going to mean that the first vertex is connected. It is not connected to itself because it's a 0. It is connected to the second one because it has a 1. It is not connected to the third node because there's a 0, and it is connected to the fourth node because there's a 1. And so on. This is for the second vertex, this is for the third vertex, and the last vertex. So for example, the 4 is connected to the first vertex, it is okay. It is not connected to the second, it is connected to the third because there's a 1, and it is not connected to each other. So the diagonal elements 0, 0, 0, 0 are all zeros because none of the vertices are connected to itself. Okay, then I'm going to implement or instantiate the Hamiltonian algorithm, and I have a Hamiltonian cycle method. In the Hamiltonian algorithm class, we are going to keep track of the number of vertices. We are going to keep track of the Hamiltonian path. It is going to be a 1-dimensional array, and we are going to store the items in the Hamiltonian path in this 1-dimensional array. And we are going to have a 2-dimensional array just for storing the adjacency matrix we have specified previously in the app.java. So that's what we are going to store here. Okay. So in the Hamiltonian cycle, we get the adjacency matrix. Because we know that it is a square matrix, which means that it has as many rows as the number of columns, which is going to get the first row and get the length, and it is going to give us the number of vertices. If you may recall, we have 4 vertices in the graph, which means that our matrix has 4 columns and 4 rows. So, whatever. Okay, I'm going to instantiate the Hamiltonian path and allocate as many slots as the number of vertices. Because of course, we can have as many items in the Hamiltonian path as many nodes in our graph. So it is a good instantiation, I think. Then we will have the adjacency matrix, of course. We get it from outside, from dependency injection. Okay. And we assume that the first item in our Hamiltonian path is the first element, the first node. So it will be the first item in our Hamiltonian path. We assume it, although you can set it to, for example, the 2 or whatever. So you can start at the node 3 or 4, whatever. Okay, and I'm going to find feasible solutions. And we start it with the index 1 because I have already specified the first item in my Hamiltonian path. It is going to be the first node, node 1. Okay, and if it's returned false, it means that there is no feasible solution, and we are going to return. If it is true, then we are going to show the Hamiltonian path. Okay. Okay, maybe it is more valid to do something like this. Maybe you will understand it clearly that if there is no solution, there is no point in showing the Hamiltonian path because there is no such path. And here, if there is no path, we just print out no feasible solution found. So we go to the find feasible solution. Okay, it's here. It's going to get a position, and if the position is equal to the number of vertices, it means that we have already visited every vertex in our graph. And if there is an edge from the last node to the first vertex, it means that we have a solution. As you may recall, in the last video we have talked about that the Hamiltonian cycle is a Hamiltonian path that has the same starting point and the end point, and that's exactly what we are checking here. If the position, and we keep incrementing the position, and it is 0, it is 1 because we have already settled the first node, and we go to the second one and try to find out that whether it is the part of the Hamiltonian cycle or not. Then we are going to go to the third one, then the fourth one, and so on. And of course, if the position is equal to the number of vertices, it means that we go back to the starting position. So we check whether it is true, and as you may recall, we have to search for ones or zeros. If it is a 1, it means that they are adjacent nodes. If it is 0, it means that they are not. So if the position -1 at the Hamiltonian path 0, which is the starting point, so the end point is equal to the starting point, and they are connected. How do we know it? Because in the adjacency matrix, they are represented with a 1. Then we return true, which means that we have a feasible solution, and we are going to show our path. Else we are going to return false, because it means that we do not have a feasible solution. But it means that this is a stopping condition, because we are going to call this method recursively. And anyways, we are going to iterate through from the vertex index 1, because we have already settled the zeros index. The 0 item is the first one. We have specified that that's the starting point. We iterate through, and if there's a feasible solution, then we are going to append it to our Hamiltonian path. And we are going to call this find feasible solution recursively on the next position, on the next element, next item, and so on. So, what about this is feasible solution? As we have talked about, there are two main criteria we have to consider. First of all, we have to check if this vertex is an adjacent vertex of the previously added vertex. Because in a graph, it's very important that in a Hamiltonian path, we have to make sure that we can get from a given point to another. So we have to check that if it is 0, it means that they are not adjacent. There is no edge between the two of them. And we are going to return false because it's not going to be a feasible part in our solution. Then with this, we are going to check, it is the second criteria, as you may recall, that whether we have already added this node. So first, this is the first part, first criteria. Whether the two nodes are connected. The second criteria, whether we have already added this given node. And if we haven't added this node, and there is an edge between the two of them, then we are going to return true, which means that it is a feasible solution. And of course, here, in this part, we just iterate through all of the vertices and keep checking whether they are good or not. Okay, so we just check whether a vertex can be added to the Hamiltonian cycle or not. And we are going to return true or false accordingly. And of course, we have to increment the position and have to call this method recursively. And as you may guess, it is going to be called, for example, 1, then we are increment the position, so it's going to be 2, then 3, and whenever this position is going to be equal to the number of vertices, now in this situation 4, it is going to check whether it's possible to to go back to the starting point. And if it's possible to go back to the starting point because there's an edge, then we are going to return true. And if not, we are going to return false because it means that it is not a Hamiltonian cycle. And of course, we will have a show Hamiltonian path method. In the show Hamiltonian path method, I'm just going to print out that Hamiltonian cycle exists. And I'm going to print out the items and the nodes in our Hamiltonian path. And of course, I'm going to append the first item of this, I'm going to append the starting point because I don't want to repeat myself over and over again, but for a Hamilton cycle, the starting point has to be the end point. So that's why it is able to append the last one because it's going to equal to the first one. So let's see whether it's working fine. Okay, I have to save it. And the Hamiltonian cycle exists. Of course, the indices are shifted because we do not start at 1 in Java and any other programming languages but 0. So this is the 0, this is the 1, this is the 2, and this is the third. So 0, 1, 2, 3, and 0 again. It is a valid Hamiltonian cycle. Now let's consider the situation, for example, this. We have 0, 1, and 2. Our adjacency matrix will be a 3 times 3 matrix, so it will have 3 columns and 3 rows. I'm going to get rid of these. And because the first node index 0 is going to connect it to the first one is going to connect to the first and the second one, then the third one, which is the 2, is going to be connected to the first one. It is good. Let's see whether it's feasible. And no feasible solutions found. Why? Because we start at 0. We visit the first one. We visit the last one. But if we want to go back to this 0, there is no edge. So we have to go back to the first one. And we are going to violate the Hamiltonian cycle property because we have to visit every vertex exactly once. And with this, we are going to visit this node 1 twice. So it cannot be a Hamiltonian path. We are not able to form a Hamiltonian cycle. And that's why, because if we have a huge graph, sometimes it is a good manner to guess whether it is feasible or not. And that's why we have discussed earlier in the topological section, in the theoretical section, that topological ordering is a very good way of predicting whether they may be a solution or not. So this is how we implement Hamiltonian cycles problem. Thanks for watching.